Hello everyone, this is the second video on pitch geometry. In the previous video, I explained briefly the pitch geometry over all types of traction and braking forces and discussed squat and lift in rear-wheel drive vehicles with rear solid axles. This video will focus on pitch geometry in front-wheel drive vehicles. The remaining drive types, all-wheel drive lift and squat and brake dive and rise, will be covered in the next videos. Before explaining pitch geometry using mathematical equations, this video will first explain how to predict the types and directions of forces acting on suspension links and springs in a front-wheel drive vehicle when driving force is applied. Later, we will analyze pitch geometry using mathematical equations. The mathematical equations presented in this video are based on Thomas Gillespie's book, Fundamentals of Vehicle Dynamics. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to enjoy new videos. Let me introduce the contents of this video. In this video, I will explain how to analyze pitch geometry when a driving force is applied to a front-wheel drive vehicle with front solid axle. First, I will explain how to predict the pitch motion of a front-wheel drive vehicle without using mathematical equations. I will explain the direction of the force acting through the link, the direction of the force acting through the spring, and then vertical force components through springs and suspension links when these link and spring forces act simultaneously. After that, I will explain how to analyze the pitch motion and vehicle attitude using mathematical methods. I will explain how to obtain the equilibrium equations of force and moment when a driving force is applied at the front wheels and how to determine the conditions for zero lift and zero pitch angle. I have a quiz for you. When a vehicle with a virtual reaction point above the ground receives driving force, which of the following correctly represents the suspension link force, spring force, and pitch angle? First, as the force acting on the suspension link increases, the force acting on the spring decreases. Second, as the force acting on the suspension link increases, the force acting on the spring also increases. Third, as the force acting on the suspension link increases, the pitch angle increases. Fourth, as the force acting on the suspension spring increases, the pitch angle decreases. Choose the correct answer among these four. This video explains pitch geometry relating to lift, which occurs when a front-wheel drive vehicle accelerates. Lift is the phenomenon of the front end of a front-wheel drive vehicle rising during acceleration. Typically, when accelerating, the horizontal driving force generated at the front tire contact point acts below the center of gravity, causing the front end of the vehicle to naturally lift and the rear end to drop. The geometric arrangement of the front suspension links to prevent the front from lifting is called anti-lift geometry. In pitch geometry, the longitudinal displacement of the vehicle's center of gravity during pitch motion is so small that it's ignored. Therefore, the load transfer between the front and rear wheels due to the shift in the vehicle's center of gravity during pitch motion is also ignored, and only the dynamic load transfer due to forward or backward acceleration is considered. Because the vehicle's center of gravity shift is ignored, the height of the vehicle's center of gravity is assumed to remain constant during pitch motion. To avoid mathematical complexity, unsprung mass and the weight of the links are also ignored. In all videos explaining pitch geometry, front spring displacement is measured along a vertical line passing through the front wheel centers, not along the actual front spring axis, as the front spring deforms under force. Similarly, rear spring displacement is measured along a vertical line passing through the rear wheel centers, not along the actual rear spring axis, as the rear spring deforms under force. Also, Kf represents the front suspension wheel rate, and Kr represents the rear suspension wheel rate. Since pitch geometry uses a bicycle model, these wheel rates are the sum of the left and right wheel rates. Let's take a closer look at the geometry of the front suspension to find the instant center of the wheel. Let's look at the kinematics of the double wishbone suspension in relation to the pitch motion. In the figure, points 1 and 2 on the upper arm are attached to the sprung mass, and point 3 is attached to the unsprung mass, the knuckle and hub assembly. Similarly, points 4 and 5 on the lower arm are attached to the sprung mass, and point 6 is attached to the unsprung mass, the knuckle and hub assembly. When the wheel moves relative to the body, point 3 moves perpendicular to the line connecting points 1 and 2, and point 6 moves perpendicular to the line connecting points 4 and 5. Find the line that intersects the plane, containing the 3 points 1, 2, and 3, with the vertical cross-section, containing the corresponding wheel center, and then find the line that intersects the plane, containing the 3 points 4, 5, and 6, with the vertical cross-section, containing the corresponding wheel center. The point where these two lines intersect is SF, and from a kinematic point of view, it is the instant center of the front wheels with respect to the body, or the instantaneous center of the body with respect to the front wheels. The point SF obtained in this way is called the virtual reaction point of the front suspension. If we analyze the rear suspension in the same way, we can obtain the virtual reaction point SR of the rear wheels that shares the rear upper arm and lower arm, as shown in the figure. However, when a front-wheel drive vehicle accelerates, the driving force is not generated on the rear tires, so the force acting through the rear suspension links is zero. Therefore, when a front-wheel drive vehicle accelerates, there is no driving force applied to the rear tires, and consequently, no force applied to the rear suspension links, so the rear suspension does not affect lift. When a front-wheel drive vehicle accelerates, the rear suspension does not affect lift, but the rear suspension springs do affect the pitch angle. When calculating the pitch angle, the wheel rate of the rear suspension must be taken into account, as acceleration causes a load transfer from the front to the rear wheels. Predicting vehicle behavior is very important in automotive engineering. Before mathematically analyzing the pitch behavior of a front-wheel drive vehicle, let's roughly predict the vehicle behavior when the driving force Fxf is applied from the suspension geometry. Since the rear wheels do not receive driving force, let's predict the pitch behavior from the front suspension geometry. First, let's analyze the forces acting on the suspension links. When the driving force is applied to the front wheels of a front-wheel drive vehicle, a force F1 is applied to the upper arm, and a force F2 is applied to the lower arm, as shown in the figure. As in the case of the rear-wheel drive, analyzed in the previous video, the ground reaction force Fz here is the ground reaction force that occurs only through the suspension links, not through the spring, due to the action of a dynamic load, and has a value of 0 in the steady state. The force Fz has a positive value and acts vertically upward when the dynamic load acting through the suspension links presses on the ground, and a negative value and acts vertically downward in the opposite case. If we calculate the vertical components of F1 acting on the upper arm and F2 acting on the lower arm, they become F1z and F2z in the figure. In the suspension geometry shown here, the action directions of these two forces are both vertically upward. Therefore, we can see that the ground reaction force Fz for the dynamic load through the suspension links is negative and in the vertically downward direction. If the ground reaction force Fz of the suspension links for the dynamic load is positive, it means that the total vertical load increases due to load transfer, and if it is negative, it means that the total vertical load decreases due to load transfer. In the example shown here, the front-wheel ground reaction force Fz is negative, which indicates that the load transfer through the suspension links occurs and the front-wheel load decreases. When analyzing the forces acting on the suspension links, remember that we use a virtual reaction point SF regardless of the location of the center of gravity. Let's continue to predict the vertical force components acting on the springs. First, let's examine the load transfer through the spring in the case of a front suspension with drive wheels. In a suspension with drive wheels, there are two load transfer paths. The first is the load transfer through the suspension links described above, and the second is the load transfer through the springs described here. For a suspension with drive wheels, these two load transfers add up to the total vertical dynamic load transfer for the vehicle. This figure excludes the load transfer through the suspension links and considers only the load transfer through the springs. The magnitude of load transfer through the spring depends on the location of the center of gravity CG and the virtual reaction point SF. This will be explained in detail later on. In most vehicles currently on the market, the vertical dynamic load delta WF transmitted through the springs acts to lift the front of the vehicle. As a result, the ride height of the front axle increases by the amount of delta F. Here, the displacement delta F has a positive value when it is a bump and a negative value when it is a rebound. Therefore, the front wheel ground reaction force delta WF has a negative value and acts in the vertical downward direction. The dynamic load delta WF is the vertical dynamic load transferred through the spring when the driving force FXF occurs in a front-wheel drive vehicle. Similar to the case of the rear-wheel drive analyzed in the previous video, the ground reaction force delta WF here is the ground reaction force that occurs only through the spring, not through the suspension links, due to the action of the vertical dynamic load, and has a value of 0 in the steady state. If the ground reaction force delta WF for the vertical dynamic load acting on the spring is positive, it means that the total vertical load increases due to the load transfer, and if it is negative, it means that the total vertical load decreases due to the load transfer. In the example shown in the figure, the front wheel ground reaction force, delta WF, indicates that the front wheel vertical load is reduced due to the load transfer through the spring. Let's analyze the vertical components of the suspension links and the spring vertical components simultaneously. Let's predict the pitch motion of the vehicle when the driving force FXF is applied to the vehicle and the acceleration AX occurs. When the vehicle accelerates with the acceleration AX, the vertical dynamic load of the entire vehicle, that is, the load transfer from the front axle to the rear axle, can be obtained using Newton's second law, the height of the center of gravity CG, and the wheelbase. The vertical dynamic load of the entire vehicle has a constant value corresponding to the driving force FXF, regardless of the suspension links or springs. When the vertical dynamic load occurs by acceleration, the vertical load on the front wheels decreases by the vertical dynamic load, and the vertical load acting on the rear wheels increases by the vertical dynamic load. These vertical dynamic loads represent the amount of load transferred from the front wheels to the rear wheels. Here, WSF is the vertical load on the entire front wheels when stationary or at a constant speed, and WSR is the vertical load on the entire rear wheels when stationary or at a constant speed. A positive delta WF indicates that the vertical dynamic load acting through the spring acts vertically upward, and a positive FZ similarly indicates that the vertical dynamic load acting through the links acts vertically upward. As previously discussed, in a vehicle with suspension geometry, like the example in this figure, when driving force is applied to a front-wheel drive vehicle, the vertical components of the links acting on the front suspension upper and lower arms also act vertically upward, and the vertical component of the spring acting on the spring also acts vertically upward. Therefore, in this case, the ground reaction force for the vertical dynamic load acting on the front wheels is negative, indicating that the direction of the force is vertically downward. The total vertical dynamic load transfer is the sum of the load transfer through the spring, delta WF, and the load transfer through the suspension links, FZ. The vertical load on the front wheels is reduced by this total load transfer. On the other hand, on the rear wheel, which does not generate driving force, the vertical dynamic load is transferred to the ground through the spring, so the vertical load on the rear wheel increases. Since there is no load transfer through the suspension links at the rear wheels, the total load transfer from the front axle to the rear axle is through the springs, and this amount is equal to the vertical dynamic load of the entire vehicle as determined by Newton's second law. In the previous video, E0001, weight transfer, we studied the forces that occur in a car during acceleration. Among these, let's review the weight transfer for a car undergoing acceleration AX. All the forces shown in the diagram and equations Fxf, Fzf, Fxr, and Fzr represent the combined force of the left and right wheels. From the equilibrium of the horizontal forces acting on the car, equation 1 can be obtained, and from the equilibrium of the vertical forces, equation 2 can be obtained. Also, from the moment equilibrium for all forces that occur during acceleration around the car's center of gravity CG, equation 3 can be obtained. From these three equations, the vertical force Fzf acting on the front wheels during acceleration can be obtained as in equation 4, and the force Fzr acting on the rear wheels can be obtained as in equation 5. The first term on the right side of equation 4 represents the load acting on the front wheels when stationary or at a constant speed, and the second term represents the load that reduces the weight of the front wheels during acceleration. Similarly, the first term on the right side of equation 5 represents the load acting on the rear wheels when stationary or at a constant speed, and the second term represents the load that increases the weight of the rear wheels during acceleration. First, let's look at the forces acting on the front wheel drive solid axle suspension links. For the sake of easy understanding, we will not consider the static vertical load acting when the vehicle is stationary or at a constant speed, but only the vertical load Fz generated as a reaction to acceleration. All the forces shown in the figure here are generated by the front wheel drive force Fxf. First, equation 6 can be obtained from the equilibrium of the horizontal components of all the forces acting on the front suspension links. The driving force Fxf must be in balance with the horizontal component of the force F1 acting on the upper arm and the horizontal component of the force F2 acting on the lower arm, which is expressed as equation 6. Next, equation 7 can be obtained from the equilibrium of the vertical components of all the forces acting on the front suspension links. Equation 7 shows that the vertical component of the force F1 acting on the upper arm and the vertical component of the force F2 acting on the lower arm, which are generated as a reaction to the driving force Fxf, must be in balance with the vertical force Fz of the front wheels. As mentioned above, Fz does not include the static load, but is only the force that appears as the reaction force generated by the driving force Fxf. Next, from the moment equilibrium, with respect to the point Q, where the extension of the lower arm intersects the straight line passing through the center of the front wheel and perpendicular to the ground in the side view, equation 8 can be obtained. The first term on the left side of equation 8 represents the moment generated by the driving force about point Q, and the second term represents the moment generated by the horizontal component of the upper arm about point Q. Solving equation 8 for F1, we can obtain equation 9 for the force F1 acting on the upper arm. Equation 9 expresses the force F1 acting on the upper arm as a function of the driving force Fxf. Substituting F1 of equation 9 into equation 6 and solving for F2, we can obtain equation 10. Equation 10 expresses the force F2 acting on the lower arm as a function of the driving force Fxf. Let's continue with the concept of an equivalent trailing arm. As explained in the previous video, E0081, pitch geometry part 1, rear wheel drive with rear solid axle, all suspension links, including the wishbone suspension links, can be replaced with equivalent trailing arms at any moment during the pitching motion using a virtual reaction point. For the front suspension links can also be replaced with equivalent trailing arms using a virtual reaction point. Substituting equation 9, which represents the force F1 acting on the upper arm, and equation 10, which represents the force F2 acting on the lower arm, obtained previously into equation 7, and solving for Fz, we obtain equation 11, which can be rearranged to obtain equation 12. Meanwhile, from the geometric arrangement of the suspension arms, the installation angle of the upper arm, with respect to the horizontal plane, the tangent of θ1, can be obtained as in equation 13, and the installation angle of the lower arm, with respect to the horizontal plane, the tangent of θ2 can be obtained as in equation 14. By substituting equations 13 and 14 obtained in this way into equation 12, equation 15 can be obtained. Equation 15 indicates that the ratio of the vertical force Fz to the driving force Fxf is equal to the ratio of the vertical component E to the horizontal component D between the tire road contact center A and the virtual reaction point SF of front suspension. The minus sign in equation 15 indicates that the virtual reaction point is above the ground and behind the front wheel, and in this case, the direction of the ground reaction force for the link force minus Fz is vertically downward, rather than vertically upward as originally specified. This means that the upper and lower arms connected to the front drive solid axle can be replaced by a single trailing arm, rigidly connected to the solid axle, with the same virtual reaction point. As shown in equation 11, the force minus Fz is the ground reaction force for the resultant force Fz of the vertical component of the forces acting on all links when the driving force Fx is applied to the rear wheel. As shown in the figure, for the front solid axle, if the virtual reaction point, SF, is behind the front wheel and above the ground reaction force minus Fz acts in the direction of reducing the ground reaction force. This time, let's look at the total forces that appear when the driving force of the front-wheel drive solid axle is generated. This resultant force can be represented by the sum of spring force and link force. The figure on the left shows these total forces. Here, WSF represents the static vertical load acting on the front wheels. G represents the gravitational acceleration, and AX represents the longitudinal acceleration. Delta WF represents the change in load acting on the front suspension spring during acceleration and deceleration. Here, delta WF converts the front spring force into a force acting along a line perpendicular to the road surface passing through the wheel center. FZF represents the vertical load on the front wheels. The total vertical force FZF acting on the front wheels can be expressed by adding the static vertical load WSF and the total vertical dynamic load as shown in equation 16. The second term on the right side of equation 16 represents the vertical dynamic load acting on the front wheels. The reason the sign of the vertical dynamic load in equation 16 is negative means that when the driving force Fxf is applied, the vertical load on the front wheels is reduced by the amount of the vertical dynamic load. Meanwhile, if we rearrange equation 15, obtained previously for the driving force Fxf, we can obtain equation 17. What we want to find is the relationship between the front wheel driving force, the dynamic force, and the change in force acting on the front wheel spring, delta WF. For a vehicle with a front-wheel drive solid axle, let's find the front spring displacement based on the front wheel center. To do this, we need to find the relationship between the front-wheel drive force Fxf mentioned above, the vertical dynamic load, and the force acting on the front spring, delta WF. Here, delta WF is the front spring force converted to the force acting along a line perpendicular to the road surface passing through the wheel center. If we calculate the moment about the virtual reaction point, SF, we can obtain equation 18. If we simplify equation 18 for delta WF, we can obtain equation 19. Meanwhile, the force acting vertically to the front wheel center, delta WF, can be expressed as equation 20 using the front suspension wheel rate and the vertical spring displacement vertically measured at the front wheel center. The vertical spring displacement relative to the wheel center is not measured along the actual spring axis, but is measured vertically from the front wheel center and means the displacement caused by the front spring. In equation 20, Kf represents the front wheel rate, and delta F represents the front vertical displacement due to front spring measured along the vertical line passing through the front wheel center. The first term in equation 20 represents the vertical dynamic load of the entire vehicle when the acceleration is ax, and the second term represents the vertical component of the force acting on the front suspension links. Since no driving force is applied to the rear wheels, the force FXFED represents the force acting on the suspension links of the entire vehicle. From equation 20, we can see that the dynamic vertical load supported by front spring delta WF is the difference between the vertical dynamic load WHGLAX and the link force FXFED. Also, from equation 20, we can see that when the vertical dynamic load of the entire vehicle is greater than the force acting on the links, the spring force Kf delta F is negative, and it acts in the direction of reducing the front wheel vertical load. Delta F has a positive value in a bump and a negative value in a rebound. Let's continue by finding the condition for zero lift in a front-wheel drive solid axle vehicle. When driving force is applied in a front-wheel drive vehicle, if no vertical dynamic load is applied to the front suspension spring, lift is zero. Furthermore, by calculating the spring displacements of the front and rear wheels relative to the wheel, we can determine the condition for zero pitch angle when driving force is applied to a front-wheel drive solid axle. The front vertical displacement due to front spring measured along the vertical line passing through the front wheel center can be calculated using equation 20, and the rear vertical displacement due to rear spring can also be calculated using equation 21, using the previously calculated dynamic vertical load supported by rear spring, delta WR. Here, delta WR is the rear spring force converted to the force acting along a line passing through the wheel center and perpendicular to the road surface. In equation 21, KR represents the rear wheel rate, and delta R represents the rear vertical displacement due to rear spring measured along the vertical line passing through the rear wheel center. First, let's examine the condition for zero lift in a front-wheel drive vehicle. From equation 20, we can obtain the geometric condition of the suspension, where the lift becomes zero. In order for the lift to become zero, the force acting on the front spring must be zero, so equation 22 must be satisfied. Therefore, from equation 20, equation 23 can be obtained. Since the driving force Fxf can be expressed by equation 18, if we substitute Fxf of equation 18 into equation 23 and rearrange, we can obtain equation 24. In order for equation 24 to be established, the expression in the parentheses must be zero, so we can obtain equation 25, which represents the condition for the lift to become zero. For a front-wheel drive solid axle, let's examine the geometry required to achieve zero lift. Based on the conditions expressed in equation 25, the geometry required to achieve zero lift can be expressed as shown here. Point G contains the center of gravity, CG, and is the point where a horizontal line parallel to the ground intersects a vertical line passing through the rear tire contact point B. Pitch geometry is analyzed based on a bicycle model. The forces acting on the left and right wheels combine into a single force at the vehicle's longitudinal center line. The vehicle's center of gravity is assumed to be somewhere at the vehicle's longitudinal center line. The black inclined line is a straight line connecting the front tire contact point A and point G. If a virtual reaction point SF exists on the inclined line between points A and G, then due to the similarity of triangles, the ratio of L to H will always be equal to the ratio of D to E, satisfying equation 25. Therefore, if the front suspension's virtual reaction point SF lies anywhere along the black line shown here, the vehicle will not experience lift during acceleration. No lift during acceleration does not necessarily mean zero pitch angle. Let's examine the relationship between lift and pitch angle. Let's examine the relationship between the lift and pitch angles of a front-wheel drive solid axle vehicle and suspension geometry using a figure shown here. What will be the relationship between lift and pitch angle when the driving force is applied to a front-wheel drive solid axle, causing the lift to be zero? In this figure, the blue line represents the vehicle shape at the constant speed, straight ahead. Zero lift means zero vertical displacement due to spring measured along the vertical line passing through the front wheel center, meaning the front ride height remains unchanged. However, as indicated by the orange line in the diagram, even if the vertical spring displacement relative to the front wheel center is zero, the rear wheel displacement is not zero, and the rear ride height has decreased. To achieve zero pitch angle, the front ride height must be reduced to the rear level, as indicated by the grey line. To lower the front ride height to the rear level, the virtual reaction point SF must be raised. Let's examine the reasons for increasing the virtual reaction point SF from two perspectives, the force acting through the spring and the force acting through the suspension links. First, let us examine the force transmitted through the spring. Raising the virtual reaction point SF reduces the vertical dynamic load, delta WF through the spring, and increases the vertical dynamic load, FZ through the suspension links. Conversely, lowering the virtual reaction point SF increases the vertical dynamic load, delta WF through the spring, and decreases the vertical dynamic load, FZ through the suspension links. We will examine the physical implications of this through equations and figures. In this figure, the vertical axis represents the vertical height, E of the virtual reaction point, and the horizontal axis represents the horizontal length, D of the virtual reaction point. The origin of the coordinate axis is tire road contact center A of the drive axle. If we replace equation 25, which represents zero lift, with the independent variable D and the dependent variable E, it can be expressed as equation 25A. Equation 25A is the equation for a straight line with a slope of h divided by L. Therefore, this equation can be represented by the green straight line in the figure. In the yellow region of the figure, the pitch geometry can be expressed using an inequality expression as equation 25B. In equation 25B, as the height EL of the virtual reaction point SF increases, the absolute value of the force FZ in the suspension links with the drive wheel increases. Since the total vertical dynamic load of the vehicle is constant, the absolute value of the spring force, delta WF, decreases. In the yellow region, the spring force, delta WF, and the force FZ in the suspension links act in the same direction. Next, let's examine the pitch geometry in the region above the green straight line. In the region above the green line, the pitch geometry can be expressed using an inequality expression, as in equation 25C. In equation 25C, as the height EH of the virtual reaction point, SF, increases, the absolute value of the force, FZ of the suspension links, with the drive wheels, increases beyond the magnitude of the total vertical dynamic load of the vehicle. In this case, since the total vertical dynamic load of the vehicle is constant, the direction of action of the spring force, delta WF, is reversed, and the absolute value increases as the virtual reaction point moves upward. In the region above the green line, the spring force, delta WF, and the force, Fz of the suspension links act in opposite directions. For this reason, if the virtual reaction point is in the region below the green line, a force extending the spring acts to increase the front ride height, and if the virtual reaction point is in the region above the green line, a force compressing the spring acts to decrease the front ride height. Meanwhile, the vertical dynamic load of the entire vehicle calculated using Newton's second law represents the amount of load transferred from the front wheels to the rear wheels and is independent of the location of the virtual reaction point SF. The role of the virtual reaction point is to determine the ratio of load transfer through the springs to load transfer through the suspension links. Once this ratio is determined, the lift and pitch angles are determined. Let's continue to look at the forces acting through the suspension links and its relationship to the zero pitch angle. The previously derived equation 17 expresses the driving force Fxf as a function of the vertical dynamic load minus Fz relative to the wheel center that occurs due to the suspension geometry when the driving force is applied. If equation 17 is rearranged for the vertical dynamic load minus Fz, equation 26 can be obtained. As shown in equation 26, the absolute value of the negative vertical dynamic load acting through the suspension links increases as the ratio of E to D increases. As the absolute value of the force acting through the suspension links, which is minus Fz, increases, the force acting through spring decreases, resulting in a greater reduction in front ride height. This effect lowers the ride height of the front axle suspension. We will examine the conditions required to make the pitch angle zero when driving force is applied to a front-wheel drive solid axle by analyzing the forces generated in the springs and links, which vary according to the suspension geometry. For simplicity, we will assume that the front and rear suspension wheel rates are the same. I will explain cases where these wheel rates are different later by deriving mathematical equations. In the suspension geometry of a typical commercially available front-wheel drive vehicle, when a driving force is applied, the force acting on the link acts upward, and the force acting on the spring also acts upward to extend the spring. The sum of these two forces represents the total vertical dynamic load transfer. Meanwhile, zero lift means that the front spring displacement is zero, meaning that the front ride height remains unchanged. However, as indicated by the orange line in the figure, even if the front spring displacement is zero, the rear spring displacement is not zero, and the rear ride height has decreased. To achieve zero pitch angle, the front ride height must be reduced to the rear level, as indicated by the gray line. To lower the front ride height to the rear level, the virtual reaction point SF must be raised. Increasing the virtual reaction point SF increases the vertical upward dynamic load transfer Fz through the front suspension links. On the other hand, the vertical dynamic load transmitted through the spring, delta WF, decreases as Fz increases. To be more specific, the vertical dynamic load delta WF that extends the spring decreases as Fz increases. If the height E of the virtual reaction point SF is on the straight line connecting points A and G, then no vertical dynamic load acts on the spring, and all vertical dynamic load is transferred through the suspension links. Since no vertical dynamic load acts on the spring, the lift is zero. However, since the rear ride height is still lower than the front ride height, the pitch angle is not zero. In the case of front-wheel drive, if the height E of the virtual reaction point SF is above the straight line connecting points A and G, the force acting through the front spring during acceleration is greater than the force acting on the spring in the steady state, so the force acting on the spring acts vertically downward to compress the spring, and the front ride height decreases while the rear ride height remains unchanged. As the virtual reaction point SF increases, the force trying to compress the spring increases, and the front ride height decreases. As the force trying to compress the spring increases, the vertical dynamic load transferred through the front suspension links increases. Using this principle, we can find the virtual reaction point location that will reduce the front ride height so that the pitch angle becomes 0. With this in mind, let's examine the pitch angle. Let's find the pitch angle when a vehicle with a front-wheel drive solid axle accelerates. By finding the displacements of the front and rear springs, we can find the pitch angle when the driving force is generated from the front-wheel drive solid axle. For the front suspension, the front vertical spring displacement measured along the vertical line passing through the front wheel center was previously found using equation 20, and for the rear suspension, the rear vertical spring displacement measured along the vertical line passing through the rear wheel center was also found using equation 21, using the previously found the dynamic vertical load supported by rear spring, delta WR, which is the dynamic vertical load supported by spring. In equation 21, KR represents the rear wheel rate, and delta R represents the rear vertical displacement due to rear spring measured along the vertical line passing through the rear wheel center. When the pitch angle pi p is small, the approximate equation tangent pi p can be used, which is equal to pi p. Here, the unit of pi p is radians. Equation 20 is rearranged for the front wheel displacement delta F, and equation 21 is rearranged for the rear spring displacement delta R relative to the rear wheel center. If we substitute these two displacement values into the second equation of equation 27, when the driving force is applied to the front wheel drive solid axle, the pitch angle phi can be obtained, as shown in the third equation of equation 27. Here, the spring displacement has a positive value in the bump and a negative value in the rebound. Rearranging equation 27, the pitch angle phi can be expressed as equation 28. The pitch angle phi expressed in equation 28 tells us that it can be expressed as a function of the acceleration, mass, front and rear wheel rates, and the geometry of the front suspension link, as we expected. Let's take a closer look at the meaning of equation 28. Let's examine the pitch angle that occurs when a vehicle with front-wheel drive and rear-wheel drive solid axles accelerates. The parenthesized expression in equation 28, which represents the pitch angle, provides important information for predicting the behavior of the front suspension. The first and second terms in the parentheses are related to the wheel rates of the front and rear axles, independent of the suspension link forces. From these two terms, we can see that the pitch angle increases as the center of gravity increases and the wheelbase decreases. Furthermore, we can see that the pitch angle increases as the wheel rate decreases. The last term is related to both the suspension link geometry and the front suspension stiffness. The larger the ratio of E to D, the smaller the pitch angle. The reason the front wheel rate Kf is included in the denominator of the last term in the parentheses is because as the front wheel rate Kf decreases, the influence of the suspension link geometry, which is the ratio of E to D, increases, and the pitch angle decreases. Equation 28, which represents the pitch angle of a front-wheel drive vehicle, has the same form as the pitch angle equation for a rear-wheel drive vehicle explained in the previous video. If we swap Kf and Kr in equation 28, which represents the pitch angle of a front-wheel drive vehicle, we get equation 29, which represents the pitch angle of a rear-wheel drive vehicle explained in the previous video. From equations 28 and 29, we can see that the pitch angle of a vehicle is greatly affected by the suspension stiffness of the axle on which the drive wheels are located. Let's continue by finding the condition for the pitch angle to become 0 when a vehicle with a front-wheel drive solid axle accelerates. In equation 28 of the pitch angle pi obtained previously, when the driving force is applied and the acceleration ax is not 0, the condition for the pitch angle pi to become 0 is that the sum of the terms in the parentheses of equation 28 becomes 0. Therefore, if we find the condition for 0 pitch angle from equation 28, it can be expressed as equation 30. If we rearrange equation 30 for the ratio of E to D, we can obtain equation 31. The first term on the right side of equation 31 represents the condition for the anti-lift of equation 25 obtained previously. As explained earlier, in general suspension geometry, the condition for zero lift is not the condition for zero pitch angle. The second term on the right side of equation 31 explains that if the front suspension wheel rate and the rear suspension wheel rate are not large, then in order for the pitch angle to become zero, under the condition of zero lift, the height of the center of gravity must be lowered by nearly twice, or the ration of E to D must be nearly doubled. From equation 31, if the rear suspension wheel rate is significantly larger than the front suspension wheel rate, the second term of equation 31 can be ignored, so the conditions for zero squat and zero pitch angle are the same. In equation 31, if the front wheel rate is the same as the rear wheel rate, the condition for zero pitch angle can be expressed as equation 32. From equation 32, if the front wheel rate is the same as the rear wheel rate, in order for the pitch angle to become zero, under the condition of zero lift, the height of the center of gravity must be lowered by half, or the value of E over D must be doubled. Let's check the explanation above with a figure. In the case of a front-wheel drive solid axle, let's look at the geometry needed to make the pitch angle zero, using a figure shown here. From the condition expressed in equation 31 obtained above, the geometry needed to make the pitch angle zero can be expressed as shown in the figure. For the sake of simplicity, let's use equation 32, which assumes that the front wheel rate Kf and the rear wheel rate Kr are equal. In the figure, point P is the point where the horizontal line parallel to the ground intersects the vertical line, passing through the rear tire contact point B, which contains the point Q at twice the height of the center of gravity Cg. To satisfy equation 32, the ratio of the height of the doubled center of gravity to the wheelbase must be equal to the ratio of E to D. The line satisfying this condition is represented by the black line in the diagram. The black inclined line is the straight line connecting the front tire contact point A and point P. If a virtual reaction point SF exists on the inclined straight line between points A and P, then according to the similarity property of triangles, the ratio of 2H to L will always be the same as the ratio of E to D, satisfying equation 32. Therefore, if the virtual reaction point SF of the front suspension exists anywhere on the black straight line shown here, the vehicle can maintain a zero pitch angle attitude during acceleration. As explained earlier, in a front-wheel drive vehicle, when the driving force is applied, in order to maintain a zero pitch angle attitude, the front ride height must also decrease as much as the rear ride height decreases. Therefore, the final vehicle attitude of zero pitch angle is that both the front and rear ride heights must decrease, which ultimately becomes the attitude indicated by the gray line. As explained in the previous video, in a rear-wheel drive vehicle, in order to make the pitch angle zero when the driving force is applied, the virtual reaction point SR must be increased, thereby increasing the vehicle ride height. However, in a front-wheel drive vehicle, when traction is applied, to achieve zero pitch angle, the virtual reaction point SF must be raised, lowering the vehicle's front ride height. When traction is applied, raising the virtual reaction point in a rear-wheel drive vehicle increases the rear ride height, and raising the virtual reaction point in a front-wheel drive vehicle decreases the front ride height. Let's briefly summarize the pitch geometry of a front-wheel drive vehicle. Using the lift-zero coordinate system explained earlier, the condition for a zero pitch angle can be expressed by equation 32a, which represents the blue line. In the regions below the blue line and above the green line, the pitch geometry can be expressed using inequality expression as shown in equation 32b. Similarly, in the region above the blue line, the pitch geometry can be expressed by inequality expression as shown in equation 32c. If a virtual reaction point SF exists in the region below the green line, indicated by yellow shading, the spring force WF acts as a force extending the spring, and the force Fz of the suspension links acts upward. These directions are the same direction in which the sprung mass is lifted upward. Ride height increases at the front and decreases at the rear compared to the steady state. If a virtual reaction point SF exists on the green line, the spring force delta WF becomes zero, and the force Fz of the suspension links acts upward. In this case, the absolute magnitude of the force Fz is equal to the total vertical dynamic load of the vehicle. Ride height remains unchanged at the front and decreases at the rear compared to the steady state. If the virtual reaction point SF exists in the area between the blue and green lines, indicated by the blue shading, the spring force delta WF acts as a compressive force on the spring, and the force Fz of the suspension links acts upward. Compared to the steady state, the ride height decreases at the front and also at the rear, but the decrease in ride height is greater at the rear than at the front. If the virtual reaction point SF exists on the blue line, the absolute value of the spring force, delta WF, is half the force of the suspension links and acts as a compressive force on the spring. The force Fz of the suspension links acts upward. In this case, the force Fz becomes twice the absolute magnitude of the total vertical dynamic load of the vehicle. As the ride height of the front suspension decreases to that of the rear, the pitch angle becomes zero. If a virtual reaction point SF exists in the area above the blue line, the front ride height decreases more significantly than the rear ride height compared to the steady state. Let's find the answer to the quiz. When a vehicle with a virtual reaction point above the ground receives driving force, which of the following correctly represents the suspension link force, spring force, and pitch angle? First, as the force acting on the suspension link increases, the force acting on the spring decreases. This is the correct answer. Second, as the force acting on the suspension link increases, the force acting on the spring decreases, not increases. Third, as the force acting on the suspension link increases, the pitch angle decreases, not increases. Fourth, as the force acting on the spring increases, the force on the suspension links decreases, and the pitch angle increases. Therefore, the answer is number 1. As the force acting on the link increases, the force acting on the spring decreases. Let's summarize this video. I've explained pitch geometry for front-wheel drive vehicles. Lift is the upward movement of the front end of a front-wheel drive vehicle during acceleration. This occurs because the horizontal driving force generated at the road surface acts below the center of gravity, causing the front end of the vehicle to naturally lifts and the rear end lowers. Antilift geometry refers to the geometric arrangement of the front suspension links to prevent the front end from lifting. To avoid mathematical complexity in the analysis of pitch motion, the following assumptions are necessary. During pitch motion, the longitudinal displacement of the vehicle's center of gravity is negligible, as it is very small and is therefore ignored. Unsprung mass and link masses are ignored. Only dynamic load transfer due to forward and backward acceleration is considered. The height of the vehicle's center of gravity is assumed to be constant. The virtual reaction point is, from a kinematic perspective, the instant center of the front wheel relative to the body, or the instant center of the body relative to the wheel. At any point on the wheel, any forces passing through the virtual reaction point will not rotate the wheel or the sprung mass. In a front solid axle, if the virtual reaction point is behind the front wheel and above the ground, a force that reduces ride height will be generated in the suspension links when front-wheel drive is applied. I explained the vehicle attitude when the front-wheel drive solid axle is driving with zero lift. Zero lift means the front spring displacement is zero, meaning the front ride height remains unchanged. With zero lift, the front spring displacement is zero, but the rear spring displacement is not zero, it decreases. I explained how to achieve a zero pitch angle. To achieve a zero pitch angle, the front ride height must be lowered to the level of the rear ride height. To achieve this, the virtual reaction point must be raised. Raising the virtual reaction point increases the downward ground reaction force in response to the suspension link force, thus reducing the front ride height. I explained how to achieve a zero pitch angle when the front and rear suspension wheel rates are the same. Under zero lift conditions, either lower the center of gravity by half, or double the ratio of the vertical component to the horizontal component of the virtual reaction point under zero lift conditions. When driving force is applied in a front-wheel drive vehicle, the conditions for a zero pitch angle are described. As the rear ride height decreases, the front ride height must also decrease accordingly. Therefore, both front and rear ride heights must decrease by the same amount. I explained the relationship between the virtual reaction point and the pitch angle when driving force is applied. For front-wheel drive vehicles, to achieve zero pitch angle, the virtual reaction point must be raised, lowering the front ride height. Increasing the virtual reaction point in a front-wheel drive vehicle reduces the front ride height. For rear-wheel drive vehicles, to achieve zero pitch angle, the virtual reaction point must be raised, raising the rear ride height. Increasing the virtual reaction point in a rear-wheel drive vehicle increases the rear ride height. I explained the relationship between the location of the virtual reaction point and vertical load transfer. Increasing the virtual reaction point reduces the vertical dynamic load through the spring and increases the vertical dynamic load through the suspension links. Lowering the virtual reaction point increases the vertical dynamic load through the spring and decreases the vertical dynamic load through the suspension links. The physical principles regarding the location of the virtual point of reaction in front-wheel drive vehicles have been explained. If CR is defined as the ratio of the center of gravity height to the wheelbase, and SR as the ratio of the vertical length to the horizontal length of the virtual reaction point with respect to the tire road contact center of the drive wheel, then the change in ride height can be determined from these. If SR is smaller than CR, the front ride height increases and rear ride height decreases. If SR is equal to CR, the ride height remains unchanged at the front but decreases at the rear. In this case, the lift becomes zero. If SR is smaller than 2CR but larger than CR, the ride height decreases in both the front and rear, but the reduction in the rear is greater. If SR is equal to 2CR, the ride height decreases by the same amount at both the front and rear, and the pitch angle is zero. If SR is larger than 2CR, the ride height decreases in both the front and rear, but the reduction in the front is greater. The relationship between the vertical dynamic load and the virtual reaction point is explained. The vertical dynamic load is the load transfer from the front wheels to the rear wheels. The vertical dynamic load transfer is independent of the location of the virtual reaction point. The role of the virtual reaction point is to determine the ratio of load transfer through the springs and suspension links. Once the load transfer ratio is determined, the lift and pitch angles are determined. The location of the virtual reaction point can be used to adjust the lift and pitch angles. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0080 Roll Center Part 12, I explained the magnitude of the load transfer distribution and the load transfer time. I explained that the force through the suspension linkage is applied first, followed by the shock absorber, and last by the spring. I also explained in detail how the difference in the transfer time of these forces affects handling in practical driving, focusing on transient turn-in. In my recent video, E0081, Pitch Geometry Part 1, I explained the similarities and differences between roll and pitch motions. I also provided a comprehensive overview and terminology related to pitch motion, explaining how analysis varies depending on the vehicle drivetrain and drivetrain setup. I also explained how to achieve zero squat and zero pitch angle in rear-wheel drive vehicles using pitch geometry. The following video will be Pitch Geometry Part 3. I will explain how to analyze lift and squat in all-wheel drive vehicle. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to see new videos. So, what are you waiting for? See you at next videos. Goodbye, guys.